I shall ask you to check. I shall ask you to check or to find the null space and range of other two operations, which are known as rotation operation, and number two, reflection operation. Try to find the null space of these two operations also. Okay, it's a bit of homework to all of you. Let us um, okay, let us now discuss something else in this session. A very important theorem. This theorem is very important, and first of all, I'm going to prove this theorem and do one sum on that. So this theorem is also very important. Let me write the statement of this particular theorem. Let capital V and W be vector spaces and let T colon V to W be linear. T colon V to W be linear if beta is equal to V1 comma V2 comma dot 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 comma Vn. B is a basis for the vector space V, then the range of T can be spanned by T beta, or it is written, or we can write it as RT is spanned by this collection of points, T of V1 comma T of V2 comma dot 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 comma T of Vn. What does this theorem is saying? This theorem is saying that if we have two vector spaces V and a vector space W over there, and if we have a basis, suppose I am considering a set beta where we have these points V1, V2 dot 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 Vn, and by all the other points of the vector space V can be generated by these points. It is the basis, beta is the basis, then you know that if I define a transformation from V to W, that is by the transformation capital T, then since I am defining the transformation from V to W, and V1, V2, Vn are the elements of capital V, so each of these points will be having images over there in the W. So TV1 will be there, TV2 will be there, and TVN will be there. Okay, all these points will be having images over here. Okay, but since these points are basis of this vector space, RT, I mean the range of T, means which is a subset of W, which is RT. RT can be generated by image of these basis points. RT can be generated by image of these basis points, image of these basis points. But you do not say that, do not think that this T beta, I mean this beta T beta set, I mean what is T beta actually? T beta is the collection of the points T of V1, T of V2, T of Vn. So they have not said that T beta is a basis. They have said that you can generate RT You can generate RT by this particular set. They didn't say in the theorem that this particular set is linearly independent. Okay, so do not consider that to be a, I mean, basis. For now, do not consider it basis. But you know, in the dimension and basis and dimension, I said that if you know the dimension of the vector space, and if you can find a basis, if you can find a generating set containing the number of points, I mean, let me write it over here. So right now, since it is an abstraction, you cannot say that this is a basis. But remember, if we know the dimension in advance, if we know the dimension of the vector space of V in advance, okay, then a generating set having elements whose numbers is exactly equal to the dimension becomes a basis. That is a different issue. If we know the dimension in advance, otherwise I'm just talking about an arbitrary V and arbitrary W. Its dimension are not known to me. So I cannot say that this is a basis. So I'm considering this to be, I'm going to show that this is a spanning set only. So I'm going to prove this particular result, and to prove this result, what I need is that proof. How to write this proof? You know that if we talk about two sets A and B, A, B are sets, then by set theoretic property, if A subset B and B subset of A, if A subset B and B subset A, this together implies that A equal to B. So to prove the given result, we need to show that, number one, RT is the subset of span of T of beta, and number two, span of T of beta is subset of RT. The proof is there in the book, but not in the way I'm going to do it. They have done it in a shortcut way. So I'm going to prove this particular result. Okay, so part one, I'm going to show that in part one, I'm going to show that RT is a subset of span of T beta. Okay, that I'm going to show. So we know that when again, it is a rule that when X belongs to A implies X belongs to B, this means that A is a subset of B. So I'm going to choose an element from Y. So let us do it. Let Y belongs to RT. This implies, by definition of RT, this implies there exists an element V in the vector space capital V such that T of V is equal to Y. Since, why is it so? Since V is an element of the vector space capital V, and as beta is equal to V1 comma V2 comma dot 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 comma Vn is a basis of V, as given the element V can be uniquely expressed can be uniquely expressed as linear combination, uniquely expressed as linear combination of points of beta. Therefore, then there exist scalars, a1 comma a2 dot 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 an in the field capital F, such that this V can be expressed as a1 into v1 plus a2 into v2 plus dot 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 plus an into vn. Now I am going to take the linear transformation from both the sides. So tv, and that becomes t of a1 v1 plus a2 v2 plus dot 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 plus an vn. And since it is linear, I can write it as t a1 into t v1 plus a2 into t v2 plus dot 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 plus an into t vn. Okay, and we know that tv is equal to y. Why? Because I have written this point over here. So y has been expressed as a linear combination of the point tv1, tv2 and tvn. Okay, so what can we say from this? Y belonging to span of the set tv1, tv2 comma dot 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 comma tvn. Okay, and therefore we started with this point which belonged to rt, and we have come to this particular point where y belonging to span of this. So by applying this result, I can say that rt is a subset of span of t of v1 comma t of v2 comma dot 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 t of vn, this. So rt is this. Next I am going to show that the reverse is true. So I'm going on to the next I'm going to next page. Probably you have written so far and you have understood, because this the logic is a very straightforward logic. So part 2 is, I'm going to show in part 2 that span of t beta is subset of rt, It would be nice if I write it also rt. You can write it rt as a subset of span of t beta. Okay, this particular thing is also very important in studying quantum computing, because this knowledge is very essential over there. And this t is actually a transformation, is tremendously important. This linear transformation, I am going very slowly with that, because this linear transformation is a extremely important topic, and you will get to see its vast I mean applications in neural network, deep learning and quantum computing. Okay, so let us now select a point. Let us now select a point x belonging to span of t of beta, that is x belonging to span of the set t of v1 comma t of v2 comma dot 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 comma t of vn. Okay, and so therefore since since this belongs to this particular span I am choosing, so there exist scalar quantities. There exist scalar quantities. Let us name these scalar quantities by a1 prime, a2 prime, dot 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 an prime, just to distinguish this from the previously assumed scalars, that this x can be expressed as linear combination of this a1 prime into tv1, a2 prime into tv2, plus dot 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 plus an prime into tvn. And therefore we can write it as this x can be written as t of a1 prime v1 plus t of a2 prime v2 plus dot 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 plus t of an prime vn, since t is linear. Since t is linear, and this can be written as x is equal to t of a1 prime v1 plus a2 prime v2 plus dot 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 plus an prime vn, since t is linear. Since t is linear, and we know that from this we can say that this is equal to actually equal to v some what was the vector I assumed in the previous case. My vector was v, so let us assume it to be v prime. Why? V prime is any vector of capital V, and beta, which is v1 comma v2 comma dot 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 comma vn, is a basis. So v prime is any linear combination of these vectors v1 v2 vn will be another vector of the vector space. So x is actually equal to t of v prime. And why? Let me write it in a proper way. So there exists an element v prime in V, such that t of v prime is equal to x, and therefore this belongs to RT by definition. This belongs to RT. And we started with x belonging to span of t beta. See this point, and we have come to this particular section that x belongs to RT. So from there, by set theoretic rule, we can write now that span of t of beta is actually the subset of RT. And from the two results, we can conclude that from the above two parts, from part 1 and part 2, we conclude that span of t beta is equal to actually RT. Span of t beta is actually equal to RT. So this proves our result. Okay, so I am going to solve one particular problem. I'm going to solve one particular problem on the basis of this. I am going to move on to the next page. Okay, hopefully you have, I assume that you have written so far. So the next problem will be the last problem of today's class. After the problem, I shall give a definition. With the definition, I'm going to conclude my today's session. So let us go into the next section, next page. The question is define linear transformation. Define linear transformation. Define linear transformation capital T colon P2R M 2 cross 2R by T of fx, which is equal to f1 minus f2, 0, 0 and f0. This question has been chosen from the book, example of the book, but the way it is given in the book, it is I think that you will not be able to guess the points. So I think that I must discuss this particular problem with you. Okay, here you see that P2R. Let us try to recall what these things are. P2R actually the vector space. P2R is actually the vector space of all polynomials, the vector space of all polynomials of degree less than 2, less than or equal to 2, equal to 2. And M2 cross 2R, M2 cross 2R is the set of the vector space of all 2 by 2 matrices, 2 by 2 matrices. Here the coefficient of the polynomial are real numbers, coefficient of polynomials are real numbers. Those who have not done problems of section 1.2 and 1.3, they will not understand what I am saying right now. If you have done the problems in the earlier sections, then only we'll be able to see what I mean to see. Here the matrix elements are real. Matrix elements are real numbers, okay. So these are the vector spaces they are talking about. So here this is a polynomial and this is a matrix, so 2 by 2 matrix. What is the basis? The basis of the vector space P2R, if you can recall, what is the dimension of P2R? Can anybody say? Can anybody say what will be the dimension of P2R? Aniket, Ayan, Dhiraj, anybody? What will be the dimension of P2R? How many elements are there in V2 in the basis of P2R? Yeah, dimension of P2R is not n plus 1. Dimension of P2R is, you say, 2 plus 1. So therefore the basis of this is 1x x square. This is the basis of any polynomial of order 2 of degree 2 or less than that can be generated by these points. Okay, this is the basis of P2R, of P2R. Okay, then what we have now, what is the definition, is what is the theorem saying? The theorem saying that the theorem was saying that if we can find a basis, of the vector space, then the range of T can be generated by the span of this image of this basis. Okay, so let us try to find, carefully observe. T beta, I have to find, T beta means collection of all such points where the elements of this basis elements image has been calculated. So TV1, TV2, TVn has been calculated. So since we have got our basis elements, we are going to calculate T1. We are going to calculate T1. We can name it as beta for your clarity. So we are going to calculate T1, Tx, and T of x square. Okay. Now, what is what is fx here? Now, if these are the basis elements, the basis elements are itself polynomials. The basis elements are 1, So we can call it as a function. This is also a kind of function. So this function is, first function is 1. The second basis element is also a function which is x. The third basis element is also a function which is x square. Okay. So carefully observe. So if we take, let us write in the next page, these are the three basis points. Okay. So now if we consider fx equal to 1, if we consider fx equal to 1, and we know that t of fx is given by this formula, f of 1 minus f of 2, 0, 0, f of 0, if I'm not wrong. Yeah. So this is the, so if fx equal to 1, then f of 1 is equal to 1, f of 2 is equal to 1, f of 3 is equal to 1, and therefore t of fx, which is equal to t of 1, that will become 1 minus 1, 0, 0. Oh, sorry, that will not be a 3, that should be 0, because here we have 1, 2 and 0. So 0, and that will be f0 equal to 1. Okay. And what is this? This is equal to 0, 0, 0, 1. Okay. Now we consider fx equal to x. Now we consider fx equal to x. Yeah, okay. Now we consider fx equal to x. Then we have got f1 equal to 1, f2 is equal to 2, f0 is equal to 0. So in this scenario, your t of fx will become t of x, and that t of x will become f1, this means 1, minus f2, that is 2, 0, and that is 0, and f0 will be 0. So that will be minus 1, 0, 0, 0. Okay. And I'm trying to write over here because all the points will be in front of you then. So let us change the color. So if we take fx now to be, if we consider fx to be x square, so we get f of 1 to be 1, f of 2 to be 4, that is 2 square, that is 4, and f of 0 is equal to 0. So in this case, your t of fx, that will be equal to t of x square, and that is equal to f1 means 1, minus f2 means 4, and that will be 0 and 0, and f0 will be 0. So that will be equal to, this thing will be equal to minus 3, 0, 0, 0. So we have got our t1, we have got our tx, we have got our tx square. So in the next page, I'm going to write all of this again simultaneously. So we get t of 1 as this matrix 0, 0, 0, 1. We have got t of x as minus 1, 0, 0, 0, and t of x square as minus 3, 0, 0, 0. Okay. So all the elements have been obtained, and therefore you see by the theorem, by the earlier theorem, we have got RT is equal to actually the span of T beta. We know this. So what will be the RT in this case? In this case, the RT will be spanned by T of 1, T of x, T of x square. And that is equal to the RT will be spanned by these matrices 0, 0, 0, 1. Okay. Minus 1, 0, 0, 0. Okay. And this is minus 3, 0, 0, 0. Okay. Now you see, carefully you see that now the matrix minus 3, 0, 0, 0, this matrix is equal to, can be expressed as the scalar multiple of the matrix this. Okay, so this particular matrix is actually can be expressed as a multiple of this matrix. So actually these two vectors, I mean, this implies that minus 3, 0, 0, 0 and minus 1, 0, 0, 0, these two vectors are linearly dependent, LD. So in the span, I am only considering those which are linearly independent. So you get 0, 0, 0, 1 and minus 1, 0, 0, 0. None of these vectors is a multiple of the other. Okay, and this RT is being spanned by this. Okay, this RT is being spanned by these two these two elements. Okay, since RT is being spanned by, since RT, the basis of RT, I mean the span set of RT contains, the span of RT contains span of RT, I shouldn't write span of RT. Span of RT is different thing. The span set, these two sets, they are obviously linearly independent, and they generate these two sets, these two elements generate M2, the all 2 by 2 matrices. So, and here also I can see that this set is generating RT. So the dimension of RT will be equal to 2. The dimension of RT will be equal to 2. Okay, so dimension of RT will be equal to 2 because it contains, spanning set of this contains 2 elements. There is a formula in the previous chapter that if a particular set S span the vector space, okay, say for S spans V, then span of S equal to V, then S becomes basis, and the dimension of S is dimension of this particular V becomes the elements present in the basis. So RT is a subspace of the vector space, and therefore RT is a kind of subspace, and RT will be, it has a spanning set. So the dimension, this spanning set is actually the basis of RT, and therefore dimension of RT equal to 2. And now I'm going to introduce a definition. You will get to know why I'm introducing this definition is very important. The definition is, let capital V and W be vector spaces and let T colon V to W be linear. T colon V to W is linear. If NT and RT, if NT and RT are finite dimensional, if NT and RT are finite dimensional, if NT and RT are finite dimensional, then we define the term nullity of T denoted by nullity of T and the rank of T denoted by rank of T to be dimensions of NT, means null space of T, and RT, that is range of T. So in other words, dim of NT, dimension of NT is equal to, is called nullity of T, and dimension of RT is called, range of T is called rank of T. And there is a very important theorem which says that, very important theorem, it is given in the book, that dimension of NT, or I should write in the following manner, that nullity of T plus rank of T, that becomes dimension of the vector space V. A very, 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 very important theorem. Nullity of T and plus rank of T gives you the dimension of the vector space. Nullity of T and rank of T gives you the dimension of the vector space. In here, my vector space is P to R. Here my V is P to R. And you know that dimension of P to R is actually 3. We know it. So we can find the nullity of T from this particular formula. Nullity of T for our previous example, and rank of T we have found it. With this rank of T is 2 and dimension of P to R is 3. Therefore, according to our previous example, nullity of T is equal to 3 minus 2, that is 1. Okay, so very important result which I have discussed. Rank nullity theorem, it is called, this theorem is called rank nullity theorem. Rank nullity theorem. We shall discuss other problems on rank nullity theorem in the next class. Probably I shall get chance with you on Monday. I shall take class on Monday in the morning, 9:30. Then I'm going to discuss rank nullity theorem, problems on rank nullity theorem, further examples and theorems on the basis of that in the next class. I think you have understood the point. Some students may have some sort of difficulties or in understanding in some logic, and they may not at present may not agree with us, but may not agree with me. But you keep on thinking of what you are doing and give some time, and you will definitely going to understand. And ultimately, to help you, I am always there with you. So with this, I'm going to conclude my today's session and hope to see you on Monday at 9:30. Till then, bye.